It's great to be back here again. Now, I spent ages thinking about the title of this talk, and then at the end I was like, fuck it, and vomited all the keywords on a slide. So basically, what we're going to talk about today is online statistical analysis using transducers and sketch algorithms. So like, a lot of this talk is basically kind of drawing from my past year building Metabase, which is a cool open source analytics tool built in Clojure. And the thing I'm specifically doing is trying to build a data scientist in a box. So what we're trying to do is kind of automate a lot of the analysis you would otherwise do working with data, and just kind of do it automatically. So that means basically doing kind of statistical analysis, among other things, on various data sources. But the thing is, like, the way you use Metabase is that you have it on-premise and connected to your data source. And these data sources can be very, very diverse. We have users with tables in the size of like 100 rows, and then we have some who have hundreds of billions of rows. And then some people have databases optimized for analytical workloads, and then some people just connect us to a Magento or some product database. So like, the problem here is that our work then has this additional twist that it has to work with this kind of very diverse set of data sources and how good they are doing various queries. And nobody will be very happy if we run some super expensive queries and then just like for a single analysis rack up a bill of a couple of $1,000s on a big query. Like, people will get upset. We've tried it, didn't end up well. So we did kind of a very kind of efficient way of doing statistical analysis. And so just kind of talk and distills some of the lessons that we've learned along the way. So let's get started first with transducers. How many of you here have heard of transducers or already used them? Everyone. Perfect. How many of you have written your own transducer? Okay, so just kind of a brief kind of overview or how I kind of see transducers are essentially transducers. What they do is kind of decomplex four things that otherwise very often tend to be complected, which is recursion mechanism, the transformation, the thing that we're actually doing with our data, building the output, and the access mechanism. So it's here kind of exploded the thing. And this kind of, the other nice part is not just kind of decomplecting all this kind of a main Clojure thing, but also that a lot of these things have either actual protocols or just kind of informal protocols of how this thing work. And that means that we can, first of all, write our own and also kind of extend existing functionality that we'll kind of see as we delve in. So just kind of for reference here, the access mechanism here refers to the fact that most kind of collection-like things in Clojure implement call reduce, which then enables the recursion mechanism, transduce in this case, to pick out values one by one or in whatever way. And then we have the actual transformation, in this case, is a map increasing by one, and the constructing output by doing conjoin. Right, so if we're kind of close to the two main protocols, and it's kind of just view it as a refresher because it's kind of, we're going to build on top of that in terms of how composition is done. So the XF protocol here is like, this is kind of a slightly abridged version of how map transducer is defined in Clojure. But the idea is that essentially, like, XF is going to take another function, this RF, presumably standing for result function or reduce function, and it's going to pass along. So basically, it's just like a lot of functions calling each other and being composed. But it turns out that this is done kind of rather cleverly and gives us great flexibility. And then the transducers themselves are kind of essentially the same thing you'd have with a reduce function, but just have two added arities, the zero arity, which is sort of as a constructor kind of thing, and the final arity, which produces the end result. Now, on this point, like, the constructor sometimes, like, it does take some creativity of what a decent constructor should be. Like here in this example of a minimum function, where we're just going to start with positive infinity and kind of with then being safe in the knowledge that anything we compare with that is going to be less than the set infinity. But then, like, where it gets interesting is how we can compose those transducers. Now, the first thing is just kind of using comp on a couple of different XFs. And here, this is kind of the vanilla usage of transducers, the one you would see in every tutorial. The thing to mind is that the order of execution is kind of the other way around as it is in most other cases when you're using compose. And then like the second one is kind of a bizarre one that I didn't even realize that it works, but like if you look at the definition, it's going to make sense, which is that you can actually compose an XF and a transducer by just essentially calling the XF and then passing the transducer, and it's going to produce another transducer where the input of the set transducer is always kind of first goes through this. So essentially what we have here is a save plus operation which works and is going to skips if you have nils in your data. And that turns out it's kind of a useful property if you kind of then move to the third thing we can do, which is use some more libraries to get more power into how we can compose our transducers. Here, the one I very much like is by Harry Granger. It's called Redux, and it brings a couple of different ways of composing transducers, but kind of the two that I like or I've used the most are post-complete and fuse. Post-complete is just the idea that we can do things at the end of it. So like if we jump back to the definition, so here when we have the end arity, which presumably does something with the result, or very often doesn't do anything, and then you can think of the post-complete as like a kind of plugin rather being the next step here, which does something with our data. And when working with kind of numerical data, it's something that you very oftentimes want to do. So for instance, like here we're taking a square of sums, and it's kind of, you can basically just reuse components of just having a plus, and then the whole result is summed, and at the end we will square root on it. And the other one is fuse, which allows us to essentially do several transformations, several transactions at the same time over the same data. So what we here do is, again, start with some dumb simple data, and then what we're going to do is like in step, we're going to construct a result having both a sum and conjoining all the elements into the end result. And like now this enables us to kind of very flexibly combine different transducers and reduce things, because otherwise you often have this unfortunate situation where you have to either have very, very inefficient computation if you always start off from the kind of, like most libraries will obviously give you things like sum of all the elements and mu and so forth. But if you want to do all those things at the same time, you either kind of have to basically write your own version of those, which does all those at the same time, or you have to do them in sequence. And like if you do it, like oftentimes it's just like not enough data, and it doesn't matter, just do them one by one and you're done with it. But like if you do kind of care about performance, that's hugely, hugely inefficient circuit. So doing something like this, where we can do it in one go, and at the same time still kind of retain this modularization and having like pieces that compose in different ways, is a huge, huge win in doing various statistical analysis. Now, and the problem is kind of this online, or that another buzzword for it is streaming analysis. So the idea here and kind of what motivates this talk is that we want to analyze data as it comes in, and we essentially never want to kind of hold it the entirety of the data set in memory. Like maybe it is, maybe it isn't, like we don't care, but generally like it's not something that we require for a computation to do. And this is obviously a very nice property to have, because it enables us to work with massive amounts of data without having to have massive amounts of memory. But it luckily turns out that many of the kind of classical algorithms can be turned into online versions, meaning versions which kind of take a single pass through data. So how to approach this if you have some kind of random algorithm? You're going to look kind of basically there are two main ways of doing it. One is that you realize that you have essentially independent computations, like in the case of, if you look at the mean, is basically we sum up the elements and then divide it by their count. And this is something that you can do in step, where you can basically accumulate the count and the sum at the same time, and then just like divide them at the end. And it's kind of oftentimes turns out that when you have various sums and so forth, if you rearrange things a bit and remember maybe some high school algebra, you can oftentimes kind of turn your algorithm into a single pass one. The other one is kind of more complicated, is that you find some kind of a recursive relation in your definition and rewrite your definition as kind of a recursive relation. There is like no really kind of one-size-fits-all formula here, and like, I'm not going to delve too deeply into calculating the variance here, but because of just like, roughly the idea is that we can essentially like this difference between the x and the mean, we can do it kind of recursively if we kind of formulate this as summing up the differences between those two. But it's something that kind of holds in some cases and doesn't, so it takes some math or alternatively some Googling to find like, does my algorithm have an online version? Sometimes it turns out it does, sometimes it doesn't, but if it does, like some of these two approaches are probably going to be how it's turned around into being online. Now, luckily for a lot of the statistical functions, you don't have to do that on your own because there are already libraries that do that. The one I like is kixi.stats, again from Harry Granger, and it comes with most of the, like, at least the vanilla statistical analysis that you would want to do, or it comes, all of these are transducers, so it's made to play nice with doing transducing, also because it's, Harry's the author of Redux, it also plays very nicely with Redux, so I do recommend you checking it out. We got a lot of mileage out of it, and even though it's kind of a very simple thing, and it's very decently performant. So kind of if we pull all those things together, we can now kind of start the glimpses of the power and elegancy of doing statistical analysis using transducers. So what we do kind of a bit more involved example, kind of pulling all these different strands together. So what we're doing is we're using fuse to calculate a couple of statistics at the same time, sum, mean, standard deviation, how many elements there are, number of zeros. Then for the mean and count and so forth, we're using functions from kixi.stats. We're even doing the composition of an XF and transducer brick, just for the sake of completeness, I guess, but it is something that kind of, like, it turns out that oftentimes that this is kind of a very useful feature to have counts of things like the number of zeros in my data set or the number of nils and so forth, so that is something that kind of comes around, and also just kind of filtering out nils is oftentimes something that allows you to reuse many of the functions where either they didn't want kind of to commit to a specific strategy of how to handle nils or just like didn't thought about it or something. So that's also a nice thing to have. And then we're also using the post-complete to when we already have some of the summary to calculate another statistic, in this case, relative standard deviation, using some of those components. So you see kind of these two play very nicely together. And here we build a map of those statistics, and then can just like get this map in and put some more data into it, and Bob's your uncle. So, and kind of, I think like for me, what this, like an example like this emphasizes is that using transducers, I think, would be kind of worth just for kind of composition alone, even if we disregard that this is kind of quite performant and doesn't spam doesn't use needlessly memory, and it's kind of very fast and just like how fast it goes through your data, but also just having this kind of abstraction where you can combine different functions is kind of a very powerful thing. Because otherwise, like, it's one of those, like, doing numerical stuff is kind of this weird paradox, because when you kind of read about it, you just like look at examples or look at kind of just library functions that this seems to be just like very simple functions, like definition of mean is very simple, definition of variance is very simple. Like, you have those small functions, but then when you start kind of putting them together, you get this mess of code, like almost like spaghetti code, even if it's written in Clojure or something. And having something like transducers massively reduces coupling and allows like a much cleaner design of, and also like it's just simply nicer to test in the end of the day, because we still have kind of like small constituent parts which do oftentimes repeat. We test it once and we know it works, rather than having this kind of chance that maybe we didn't think of some edge condition, or maybe what happens if there are nils here and then like something explodes or so forth. And here we can just have like well-defined, well-tested components and use those. Now, sadly, not everything is great when using transducers. Like, there are a couple of annoyances. They're pretty minor, but still, again, would very much like if this were solved at some point in the future. Alex Miller, are you listening? The first one is that you can only transduce one collection at a time. This kind of sucks oftentimes. Like, it's something that I would often want to kind of do two or something at a time, like you can do with map, where you just pass it however many calls, and here you can't do that, or you have to go through map with a vector, but that kind of defeats half of the purpose, which is gaining performance. Like, you still get obviously all the benefits of decomposition and so forth, but just in terms of performance, if you have to create those intermediate pairings, so it's just one call, that's kind of sucks. Then you always have to pass in an XF function, which is kind of, oftentimes you'll see kind of, for my taste, there's too much code which goes transduce identity and then something. And it's like, so this kind of repetition of identity, I mean, like, it's not a huge deal breaker. Like, sometimes you maybe mess up and forget it, and then the whole thing explodes, or perhaps because you have wrong arity. But it's kind of, it feels like there should be an arity of transduce with one less argument, so you can just like say, okay, XF is going to be identity and be done with it. And the last one is that, and this one is kind of specifically for the core functions, that having functions that return a transducer or not, it can be very error prone, because again, you forget some argument, or you first have some version with threading and then kind of refactor it to something, and then kind of oftentimes you have basically call a map which returns a transducer, and like it seems okay, but it actually does completely wrong thing, where it explodes in a not obvious way. This, again, here is not helped by Clojure's error messages. So it's going to be something to keep in mind. It's not a huge problem, but it is something that, like, I will confess that occasionally, like, I'm being carried something and it does bite me, and it is annoying. Right, so this is kind of part one, like a love song about transducers and how great they are, but sometimes even that's not enough. Like, they are performant, but we can do better. We can do much, much better. And this is where sketch algorithms come in. The idea is kind of, like, this is like a huge family of different algorithms. We're going to, like, here we're going to look at two, but there are a number of them, and it's a very active field of research. So, like, the idea is that you summarize your data with the data structure and then query that data structure rather than working on your data directly. So we summarize or sketch our data and then work with this sketch. The first algorithm we're going to use, and the one that I get by far the most mileage of, are histograms. Now, at least in a kind of visual sense, how many of you know what a histogram is? Okay, the majority. But so kind of just for a few who don't, like, the idea is, like, essentially what you get if you call Clojure function frequencies, which gives you values and their counts. That's kind of a histogram. So it's an idea of having different buckets and then counts for those buckets. And like either it can be just like one value per bucket, or a bucket kind of spans some area and then again has counts. So they can have like different, you can think of like different resolutions where kind of the wider the buckets, the lower the resolution, and the bigger the kind of the approximation aspect of it is. So how we kind of like, there are different ways of doing histograms. We're going to look at like one that's pretty representative and also kind of a rather good one. So the idea is that we're going to, like, in advance, we're going to fix the upper bound of how many buckets do we have. Okay, so like, okay, at the maximum we're going to have 64 buckets or 128 or whatever. Okay, and then for each incoming value, we first look at, like, do we have a bucket that already this has, like, that's at exactly the same point as this value that came in. If it is, cool, we'll just increment its count by 1. If not, we're going to add a new bucket positioned where the value that came in is, and say that the count is 1. But now, if we already had the maximum number of buckets before, we now have a problem because we have k plus 1 buckets. So what we do now is we'll have to merge 2 buckets. So we are again down to k buckets. And the way we do that is that we sort all the buckets and we find the two that are most adjacent, like the closest, those closest together, and we merge the two the two into one, essentially kind of doing a weighted interpolation based on how big the count is on one and the other, and we're again back at k. And this is kind of repeat over and over again. The nice property of this is that the same way that you can add values, you can also just merge entire histograms. So instead of kind of like, if we say we had a bucket with count 1, instead of 1, the count could also be thousands or millions or whatever, and this allows us to merge histograms whenever. And that turns out to be very, very nice property. First of all, it allows you to, even if you want to go into really massive amounts of the data, you can do this completely parallel. Like, it's a perfect algorithm for map reduce. Just kind of reduce it over a huge number of histograms and then start merge them. But there are also kind of other uses in which we'll delve into in a moment. But first, just kind of for completeness sake, let's look at how you actually use histograms or kind of estimate the values from a histogram. Depending on the implementation, they're usually going to be making some assumptions. The version I'm talking about, and it's also used in the library that I'm going to show you later, assumes that the bin mean is also its median. So the bin mean is basically the point where each of your bin is centered, and the assumption is that of all the points that fall into this bin, half of them are going to be less than the medium, this point, and half of them are going to be more. So it's going to be exactly at that center. So like this property, like you can have pathological data where this doesn't hold or something, but like in practice, I didn't find a lot of kind of very pathological cases where that would be a huge issue. But it's something kind of to keep in mind, and also it's good to have in mind when you think about how the estimating values works. Okay, so this is our assumption. And then what we do is that essentially we're going to do some sort of a weighted interpolation between our bins. So like if we need some point somewhere between the two bins, we're going to say, okay, we know it's somewhere in between here, and then like we're assuming it's like they're half the points from one bin are on the side, like so it's going to sort on the area intersection between half the bins from one and half the bins from the other one, and then just going to do the weighted interpolation based on the count of elements in both of those buckets. Roughly. Like again, here there are different tactics of how you can do this, but to gain kind of a intuition of how this works, this kind of, I think is a decent working model. And sometimes the nice thing is that for some operations you don't even have to kind of you can have like you have relatively well bounded the how much you're approximating, because you can be kind of precise up to a certain bucket. We know, for instance, like if you want to know what's a cumulative sum up to some point, you can kind of like find the bucket, the biggest bucket that's still less than my point, and up to this point we know the exact count, and then we just kind of have to estimate a little bit over it, and that again helps with precision. Now, what kind of the other nice thing that doing a sketch like that does is that it kind of even further decouples data collection from computation. Now, we've already seen when talking about transducers that they kind of decouple the data access and so forth, but still what they don't do is like once data starts streaming in, that's it. Like you can't do anything with that. Just like a transducer is like completely reactive in a sense, just like reacting to the data coming in. While what something like a histogram does is that it enables you to actually capture the data and it holds it as such, and the data here kind of becomes essentially a first-class object, but massively compressed, and that allows you to do things like persist histograms and move them around and so forth. So just like first a quick view of how this kind of put together works. So, the library I very much like when using histograms from Clojure is from BigML called histogram creatively, and basically here what we do is we wrap the creation, which is kind of a bit too imperative for my taste, into a transducer, and then build, so we kind of build a histogram from a transducer, and then you have various functions that you can call in this histogram that estimate things. Like in this example, we have variance and then percentiles, minimum, maximum, median, and so forth. And there's like a bunch more things that this histogram can do. Kind of as a quick aside, like I find this kind of pattern of wrapping kind of Java construction or some very imperative steps in a transducer is kind of a very nice pattern because it removes all this kind of nestedness and does ensure that all the kind of methods are called at the end and so forth. Like this is one of the better cases of how we can use the one arity aspect of a transducer to just kind of do any last steps or closing streams and so forth. So to kind of, even if you don't have a problem that's like very obviously a transducer problem, but if it has kind of a construction, you know, like oftentimes Java libraries will have this kind of annoying way of setting up properties like one of the other, and it's kind of this reduce-like operation. Wrapping in a transducer is going to be like a much nicer Clojure API than fighting with that. But like now back to our main story. So once you have a kind of a histogram, it turns out that it's very, very convenient to have distributions readily available everywhere. It's the same thing like, I always say like when talking about data analysis, always kind of think in distributions, not specific numbers. Because it's like, no matter what, like, no matter how many descriptive statistics I give you, there's always kind of some uncertain, like there can be like different data sets that fit those statistics, and like you don't have such a clear view of what's actually going on. While if you just look at the distribution, it's pretty clear what we're dealing with, and it's actually much easier to spot things like outliers, and we have like a fat tail or a thin tail and things like that that can otherwise very often get obscured, or it's even quite hard to model them nicely if you don't kind of make some other strong assumptions. So kind of try to work with distributions, visualize them, but it turns out that kind of the same thing also applies when kind of doing just computations, that if you have something that's kind of a distribution, that's a very nice thing to do. So kind of some of the things that you can kind of maybe not obvious that you can do with histograms. Like first of all is that because it essentially summarizes the distribution of your data, you can sample from it like it was a distribution. And that kind of turns out to be rather nice. Like one thing is that you can do is that you can first summarize your data, and then even if you want to run kind of different algorithms that maybe are like can't be turned into a completely online version, so they are O and N of N square or even worse, what you can do is you first summarize your data and then run your algorithm just on a sample of that data sampled from your histogram. And it's kind of nice because you then have very, you know what your runtime is going to be because I want 1,000 samples, and that is, and you can kind of even, because like histograms aren't precise, you can actually even use that to generate a larger data sample than you have. So it acts as sort of like a perturbation to your data, which is kind of a trick that you sometimes would use when kind of trying to make some machine learning work on a relatively small data and say, okay, I'm just going to kind of add or detract a slight amount of noise from my data, and by that kind of enlarging the data set. Like if you assume that you kind of nail the distribution right, and here you can kind of you get this out of the box for free. The other thing is you can do, once you kind of understand what your distribution is, that you can kind of do, for instance, stratified sampling if you want. Just kind of maybe you're just interested in what's happening in the 19th percentile and just like sample from that and analyze that rather than having to work with data. So like oftentimes kind of it's beneficial to have this intermediary of kind of first assembling a distribution and then working with that distribution. There are some kind of limitations if you want to kind of work with multiple variables at the same time. This is kind of somewhat alleviated by the concept of targets, if you look at the histogram library that I talked about, but it's kind of to keep the the scope not exploding. Let's just kind of keep this for something that you can do on your own time. The other kind of nice thing that you can do is essentially kind of time slices. We already talked about how you can kind of willy-nilly merge histograms and sort of essentially slice your data any way you want and put it into histograms. So one thing that oftentimes kind of is a very good thing to do is if, let's say, you have some kind of time series data, and you just kind of collect time slices of maybe an hour or a day or something, and then you can kind of compute various statistics on it, and then what you can do is you can look at the various trends of how those things changes. Now, if you think about something like, I want to see how my variance is changing on a day-per-day basis, like what the trend of the change of variance is. That's kind of something that's relatively hard to compute if you just kind of start from scratch. But here, if you're just kind of smart and you're just like saving or have some ETL process that generates a histogram for each of your daily data, you can just kind of calculate that, and use the histograms. And then, of course, you can also kind of merge them or split them however you want. So you can kind of pick the different resolutions and go up the resolution scale if you want, so forth. So again, something to keep in mind is oftentimes it makes sense to create kind of snapshots of your data and then work with that. So kind of finishing off, like most of it we're talking about till now was working with numerical data. What about categorical data? There are kind of a couple of answers. Like most histogram libraries will have some way of also working with categorical data. How well depends on the library. Again, I mentioned this concept of targets, which essentially is kind of this coupling of number value with something else, the target, which can be another number or a category. It's something that you kind of get out of the box, for instance, out of the histogram library. And that kind of can take you a long way, but it still has kind of the limitation that you actually then have to hold all the categories in memory. But I'm just going to wrap it up. What about kind of the cases where we have millions or hundreds of millions of categories? For instance, like some statistics about web pages or something like that, where we have like a huge amount of categories and a very long tail. Well, there is also a sketch algorithm for that, and it's called account min sketch. And here is a sketch of the set sketch algorithm. It's rather simple, so it's kind of best to show it in code. Basically, the idea is to have to build a grid. So we have a vector of vectors, and then for each row also have a hash function. And then, like, the idea is that the hashes are kind of universal hashes, meaning they kind of have some nice properties when they play together, and they're kind of more independent than if you just kind of generated a couple of random hashes. And so what we do is that whenever, so this is like our so we have a vector of, again, vectors, and for each row we also have, we get a hash function. And then what we do is when a new element comes in is that we essentially go through all the hashes and calculate the hash for that element, and then increment each column in that row. So essentially, if let's say you have 100 rows and a new element comes in, we're going to increment 100 elements in our grid of +1. And that's about it. So what then happens is when you want to estimate something like frequency, you're going to take an element, again, calculate its hash, and then just like look at all the values in where it, all the points on the grid into where it would fall, and pick the smallest one. Now here, obviously, what you're going to say, hey, but this is probably going to be like grossly overestimated. And the answer is yes, sort of, but it turns out that oftentimes like you don't really care that much about absolute precision. That very often, like if you think what we are doing at the end of the day is that we are comparing things. So you are just interested in kind of relative things, or oftentimes just want to know what's kind of my top 10 of something or something like that. So in a lot of those cases, you can actually throw away a lot of the precision and just instead have something that's quite efficient. And this is kind of the idea here. It's also like you can, like, there are some guarantees in terms of the biggest possible mistake and its probability and so forth, which are related to the size of the grid, so you can kind of calculate that, and you do actually have precise error bounds if you want, it's kind of worst case error bounds, and then kind of in practice it turns out that oftentimes it kind of works much better, especially if you consider the actual use cases rather than just kind of using it for all the values. But if you look at how you do it and you actually using it, oftentimes the errors you can get are much less. If you want to kind of play with other this kind of streaming sketching algorithms, this is kind of a decent Java library. I've played with some. Don't take it as a strong recommendation as the others in this talk because I've used it much less, but from what I use it, it kind of seems solid, so have a look. Right, and now kind of wrapping up, it's like I think kind of the main things that I would like you to take away from this talk are, one is that kind of transducers are a wonderful thing, and not just for their performance benefits. Maybe like even the performance benefits are the least. I think just the element of composition and decoupling or decomplecting, if you want, that they bring into development is a huge, huge win. Second one is like you don't realize how often you want to actually be working with a distribution rather than with just like raw data or summary statistics until you actually have them kind of readily available. It's like one of those things that where tools are shaping our thoughts. If you have a tool where it's something like which has this affordance of distributions, you're going to end up using it much more often, and you're going to see how many problems can be solved much more elegantly than if you don't have this available. And oftentimes, like this does imply a certain level of approximation, and oftentimes, or actually more often than not, this kind of level of approximation is perfectly fine. Kind of do understand your problem, and there are some cases where you don't want to be approximate, but oftentimes it's good enough. And you can have like massive gains if you then use approaches that embrace this approximate nature or estimating nature of computation. And last but not least, like if you put all these things into practice, transducers, sketch, and so forth, it turns out that you can come like surprisingly long way on a single machine. Like you don't need grids and Spark and so forth, but it's like a laptop or it's like a single thread on a server, and you can do kind of remarkable things. And with this in mind, if anyone has any questions, or just track me down sometime later and ask me, like obviously I love talking about this, so.
Thank you so much. Questions? We have time for maybe one or two. No? Oh, no.
Hi. Yeah, you mentioned that you would like to have a version of transduce that doesn't take the cross form. What's the difference then with reduce? I thought that was basically what transduce was versus like reduce with an extra parameter.
I don't think it uses the entirety of the transduce protocol as such. Like the function you would pass in reduce doesn't have the two additional arities. It just has the 2-argument arity, and that kind of like, because of this story of composition and so forth, it kind of like you want those 2 arities as well. This is kind of, I guess, another, if you like want to talk about words, like another one is like this, precisely this difference also in the reducers library, which kind of preceded transducers, and there you have essentially one protocol of what a reduction function is, and in transduce you have another one, and like they don't play very well together. And then you even have like helpers like monoid from reducers, which is kind of helpful because it gives you the constructor arity, but then you don't have some way of constructing also the other necessary ones. So it's kind of, like this is the thing I guess that kind of sort of sucks with Clojure, is that you have those also like amazing ideas that are kind of then done 95%, but like at the last 5% of polish of how all the things kind of should work. And like the same thing is like why like many of core functions already have the kind of the 0 arity and the 1 arity or something, or just the 0, but like some of them don't. And like it should be so much nicer if someone took the time and just like added the 0 arity everywhere, and then it can like the transducers would suddenly become much more efficient to use, just efficient in the sense of number of keystrokes I need to press in order to get the desired effect.
Okay, makes sense. Thanks.
Any other questions? Okay. I think we have another 14 minutes for the next talk, so stretch yourself and then grab some fruits, and we'll be calling you back in again for the next talk. Thank you.